Wonderful. So we're very happy to have Andreas here, Andreas Crivellin. He's going to tell us about all the cool things that are happening and that you can do with flavor physics, and he's an absolute expert on the topic, so we're lucky to have him. Take it away, Andreas.
Thanks a lot for the invitation. I'm very happy that I can tell you about my beloved topic on discovering new physics with flavor. So as you see here, I'm usually with the Paul Scherrer Institute, which you can see here at the University of Zurich, which would be somewhere on the back here. But currently I'm staying for scientific associateship at CERN. And as I said, there's not so much difference, still the mountains in the background, but everything is just much, much bigger at CERN. So, as I said, I want to talk about discovering new physics with flavor, and you already can see there's some twofold meaning here. So, the flavor you discover, the new physics you discover, you don't only do it with flavor, but I think also the new physics is flavored in the sense that it's very interesting, colorful, and I would say definitely something unexpected. So, I mean, if the flavor anomalies are confirmed, the origin of them must be something much more exotic than, for example, the MSSM or a composite model. So it would definitely be surprising and point into something in a completely new direction, which I also think is very nice. It's more exciting than discovering something you already expected. So I will start, of course, with the introduction, and then I will talk about some of these flavor anomalies. So there are at least 4 main of them. One is B2S mu, B2C tau nu, the anomalous magnetic moment of the muon and the electron. But I would also like to point out that this observable, which we call RVUS, can also be interpreted as a sign of lepton flavor universality violation. Then I come how one can explain these flavor anomalies. First of all of them separately, and then how one can look for common explanations, where I definitely like Leptoquarks, as you can see here. Okay, so let's start with the introduction. Very basic, you all know about this, but I think it's still very important to keep this in mind, because we haven't found any new physics directly at the LHC, so from time to time, one might get a little bit desperate and wonder, is there really physics beyond the standard model? But the good news is, if we take a step back, we all see the standard model cannot be the final story. So it's, in fact, what we have in the standard model can only account for something like 5% of the matter content of the universe. So we know that dark matter is there, and the general thing you do is you introduce a new weakly interacting particle to account for it. We also know that neutrinos are not exactly massless. And again, the easiest way, I'm of course not saying it's the only way, the easiest way probably is to introduce a right-handed, or what is also called sterile neutrinos, so that you can write down a mass term. We also know that everything around us exists. And for this, if the Big Bang was symmetric in matter and antimatter, you need a mechanism to get this matter-antimatter asymmetry. And one of the criteria for this, one of the Sakharov criteria, is that you have additional CP violating interactions. So even though in the standard model, you know, we have this one complex phase in the CKM matrix, which is even close to maximal, the CP violation within the standard model is by far not sufficient to explain the matter-antimatter asymmetry. So you in general introduce new CP violating interactions. So all this tells you the standard model definitely must be extended, but it doesn't really tell us about the fundamental underlying theory, because there are many possibilities how to realize this. And what is even worse is it doesn't tell us about the new physics scales. Because dark matter, you can do it anywhere from the KeV to the multi-TeV scale. For right-handed neutrinos, it's even worse. You can do it from the KeV up to the 10 to the 14 GeV scale, and also the matter-antimatter asymmetry. If you don't insist that it is electroweak baryogenesis, so where you use the electroweak phase transition, then you also can do this at nearly any scale. So you don't know where this new physics, even though it must exist, lies. And this then for this reason, we need to combine several frontiers in order to find which theory can supersede the standard model. So we have the cosmic frontier. This is, of course, dark matter, dark energy, cosmic rays, and neutrinos. Then the energy frontiers, this is in principle at the moment only the LHC, but we are, of course, hoping for future colliders. And then there is the intensity frontier. Here, of course, at least for me, most importantly, we have Flavour, which is a great tool to search for physics beyond the standard model, but there is more. There's neutrinoless double beta decays, test of fundamental symmetries like Lorentz symmetry, but also proton decay. But the important thing here is these three frontiers are not really in a competition to each other, even so, of course, every frontier wants to find new physics first. They are also very much complementary because you can test new physics in different ways. So take Flavour, where I really hope that there is new physics, then you will also be able to see these new particles, which give rise to these Flavour anomalies at high energy colliders, but of course it can also be related to dark matter, and maybe you see it in cosmic rays and so on. So it's really good that we have all these different frontiers, and by combining them, there's some good hope that we can really map down the theory superseding the standard model. So as I said, we want to find new physics, and here I want to focus on Flavour. So let's look at it in a very, very simplified way and say, how do we do this? So what one does here is at Collider, so one produces many, I think 10 to the 14 is the record by Mach, heavy quarks or leptons. And as I told you in the introduction, all these heavy quarks and leptons are unstable, and they rapidly decay into light flavors. And then what you do is you take your experiment, you do the analysis, and then you compare it to the standard model prediction. And if they don't agree, the logical conclusion is that there must be new physics. Of course, under the strong assumption that no experimentalist and no theorist did a mistake here. But otherwise, it's like the saying from Sherlock Holmes, if you excluded all other possibilities, the remaining one, no matter how improbable it is, must be the correct one. So if experiment and standard model really disagree, then no matter to which exotic new physics models they point, there must definitely be new physics, even so our sense of naturalness might tell us that we don't like it. We, in principle, don't have a choice other than believing it. And what this plot here on the right-handed side tells you is that it's really possible that you can find new physics first with Flavour observables before ever discovering it directly at the LHC. Of course, I have to admit here, this is under favorable assumption for flavors, namely that you have large generic sources of flavor violation, and here for epsilon k, which is CP violation in the kaon system, you even have a large CP violating phase. But otherwise, what you can see here, you can test higher scales with flavor than what you can do directly at the LHC. And the good thing about this is that that it's also on the other hand possible that if you observe new physics in the flavor sector, this is possible because it's not yet already ruled out by LHC searches. And in fact, this is always what happened in probably the last 4 to 5 decades. We always knew to some good approximation that there must be new physics before we observed it directly at a high energy collider. For example, we knew that something like the W boson exists because of Fermi interaction. We knew to a good approximation the Higgs mass because of electroweak precision observables, and so on. And now the hope is that history repeats itself, that we might find new physics first in flavor observables before we then find it directly at at the LHC or a future high energy collider. Okay, so this here is the global fit to the CKM matrix. And what this just tells you is that the picture that the CKM matrix, and so the W interactions are the main source of flavor violation, is well established. So here in this plot, you see all these different ways how you can determine what is called here this unitary triangle. So because the CKM matrix is unitary, you have several ways to define unitary triangles. This here is the standard unitary triangle, which is chosen because the sides of the triangle have a length which is of the same order. And then in this way, you can nicely show these different bands. So here, this is the determination of the CKM element VUD. This is BS and BD mixing. And then also these measurements of the different angles here. And you see they nicely overlap in one point. This doesn't mean there's no new physics. It only means that new physics in these observables here, which is tree level, including light leptons, and delta F equals 2 processes, that here new physics cannot be large. It can still be of the order of 10, 20%, but it cannot be orders of magnitude bigger than the standard model. And very importantly, when I talk about the other flavor anomalies later, they are not included in this global fit here. Okay, so this brings me then to the overview on the flavor anomalies. Do you have any questions so far? Please interrupt me at any time if there are questions. Don't wait till you get lost. Okay, then let's continue with the overview on the flavor anomalies. So with anomalies here, I don't mean something like gauge anomalies, where you have these divergences within 3 or 4 gauge boson interactions. Here with anomalies, I mean a measurement which disagrees with the standard model prediction. And the first class of process where we observed such anomaly is B to S mu plus mu minus processes. So this is what is called a flavor changing neutral current, because the B quark and the strange quark have the same electric charge. Now you remember the only source of flavor violation in the standard model is the charge W boson. So in order to construct a neutral current, you need to have a loop effect. There is no other way to do it. And this is also the reason why all flavor changing neutral currents in the standard model are strongly suppressed. So you have this loop factor, which is something like 1 over 16 pi squared. You have a suppression by the electroweak scale because of the heavy W boson compared to the light external B quark. And it's also suppressed by small CKM elements. You remember from the introduction that the CKM matrix is hierarchical. So the further you go away from the diagonal, the smaller the elements become. So this B to S mu plus mu minus processes are strongly suppressed in the standard model and therefore very sensitive to new physics. Now, what do I mean with processes? So there are these diagrams here, which generate then in the end this effective BS mu plus mu minus interactions. So since everything here in this loop is heavy compared to the external states, what you can do is you can integrate out all these heavy particles, and then you remain with a point-like interaction of BS mu mu or LL, which you cannot resolve in these experiments because the energy is too low. And then these effective interactions, which are induced always by the same kind of Feynman diagrams, they contribute to different processes. So with different processes, you can measure the same effective interactions. And now I will come to some of these different observables which all depend at a fundamental level on the same effective interactions. So probably the easiest thing you can look at is b sub s to mu plus mu minus. So you see here, you have a meson in the initial state, a lepton pair in the final state. So you can already see initial and final state don't interact with QCD. So this is quite good to calculate this on the theoretical side. In fact, you can do this whole calculation in principle perturbatively. You only need the BS meson decay constant for it. However, the problem here is the muon pair must have opposite chiralities because the BS meson is a pseudoscalar one, so it's chirality suppressed by the small muon mass and has a quite small branching ratio. So therefore, it is statistically limited. And this here you can see here on the right-hand side. So here's the branching ratio of b sub s to mu plus mu minus. So this is in units of 10 to the minus 9. And you see here, this is the standard model prediction. This is what the combined average from CMS and Atlas tells you. CMS and LGB tells you. This is the Atlas measurement. And you see here, they are somehow something like 20% below the standard model prediction. But as I said, it's statistically limited. You could also look at the case like b sub s to phi mu nu. So phi is a SS bar bound state. So this is also a B to S transition. But here you see this is a semi-leptonic one. So you have mesons in the initial and in the final state. So they interact via QCD. And such a process you cannot describe anymore only by the decay constant. You need something which is called a form factor. So a form factor is a momentum-dependent quantity which describes you the probability for a BS meson converting to a phi meson, depending on the momentum transfer to the muon pair, which you call Q squared. So here, this Q squared is the invariant mass of the meson pair. Now, calculating this process, therefore, is not that easy anymore. You need some non-perturbative methods for these form factors, like lattice QCD, or also light cone sum rules. So you have some intrinsic errors which are not so small. However, what you can see from this plot here is that the measurement, these black crosses, are all below the standard model prediction here in these boxes. So these two seem to agree, and they point to something like a deficit of 20% here. With this alone, probably you will not get very excited, but there are other observables. So there is this famous P5 prime anomaly. Maybe you heard of it. Many people say P5 prime is the worst name ever given to an observable. And even though I'm a good friend of Joachim Matthias, who invented this, I cannot really disagree with the statement. But despite of the name, which is really terrible, P5 prime is a very nice observable. So what is P5 prime? P5 prime is an angular observable in B to K star mu mu, where you have the polarization plane of the K star and the polarization plane of the muon pair. And then you can define different angles between these polarization planes. And P5 prime is defined in such a way that the dominant dependence on the form factors, which you need to calculate B to K star mu plus mu minus, again, because it is a semi-leptonic decay, drop out to a good approximation. So this is why you get these reasonable errors here, which are again the boxes within the standard model, while the measurements here are somehow again above the standard model prediction. But don't be mistaken, before it was below, now it is above, but this is still consistent because it's a deficit. You see, the measurements are closer to zero than the standard model prediction, so it again points towards a deficit. So there are many colorful crosses here, but in principle, it's mostly dominated from the LHC-b error. And then if you look at the update here, it's getting even clearer. So you see they are lying on a nice smooth curve. So this doesn't seem like there's something odd going on with the measurement. And again, if you combine this, you arrive at something like a 3 sigma deviation from the standard model.
The DHMV is some lattice calculation?
No, this stands for H was Hofer, Matthias Virchow. This is Hofer's Matthias Virchow. It's not, so they use lattice QCD input, of course, but there's also more that you have to take into account, like this non-factorizable contributions and the problem with the charm resonances.
So we don't really know the error bars.
Sorry?
We don't really know the error bars.
No, we know the error bars. All this is included in these error bars.
But you have to do something about some things that you cannot calculate.
I mean, you can calculate, of course, the form factors, and then you have to make a reasonable assumption about the errors of the form factors. So this is
what's reasonable? How do I get the error bars on what's reasonable or not reasonable?
I mean, this is how you do it in lattice QCD. So they have their intrinsic errors coming from, for example, if they use staggered fermions, and then they also have their statistical errors, which they can estimate, and then they can provide you with an error estimate for their form factors.
I'm sure they're doing best they can, but I'm just saying that it's not a completely clean observable.
It's not a clean observable, but the errors should be conservative, and they should really include in a reasonable way all uncertainties. So if you quote this 3 sigma deviation, you already took into account that this observable hasn't such a clear theory prediction like other observables. So many people say, oh, I don't care about this observable, it's not clean. But I don't think this is a fair argument, because the point that it's not so clean has already been taken into account in the standard model prediction.
I think you cannot really completely take into account how unclean it is.
Sorry, you cannot completely take into account?
Something unclean, right? How can you completely take that into account?
I mean, if you...
Why is this value reasonable? Why did I multiply by 2 unreasonable? What's the measurement measure?
It applies to any theoretical calculation, no? How do you estimate a higher order, a missing higher order contribution?
No, but there are, like you said, you have to make some assumptions about the non-perturbative parts, right?
Of course, you always have to make these assumptions, that's clear. But why shouldn't this assumption here? But these assumptions are not questioned in other observables. So why should they be wrong here, while they are commonly accepted in other observables? Well, you make the same assumptions as when you calculate many other observables where people never question these assumptions about the errors. And I mean, the assumptions on these non-factorizable contributions and so on are already quite generous. It's larger than you normally expect them to be.
Yes. May I ask a complementary question? So then I see from the figure that you are showing in the plot that there is no standard prediction from DHMV at the higher Q squares.
Yes.
Is that a technical problem? What is? And there is, however, a very high Q square prediction from the other group. Yeah.
I mean, that's a question of how conservative you want to be. So you see that the DHMV is much more conservative than ASZB, because here you see these errors are all bigger here, and they are even so conservative to say we don't want to go too close to the charm resonance here. This is why we don't include this bin at all, and we also don't want to say anything at a very high Q-squared bin. But even if you take this very conservative estimate of DHMV, then you have 2 times nearly 3 sigma here.
Okay, very good. Thank you.
Okay.
Could I ask an experimental question? Could I see the formula for the P5 prime anomaly?
The formula is very complicated. It's several lines. I didn't put them here.
Yeah, well, that's why it's an experimental question. I'd love to see it just to know what it is.
you can, I can send you the link to the article, then you can look at it. But I mean, it's quite complicated with all these different angles and so on. It's not that you, I mean, this observable wasn't constructed in such a way that you can easily measure it. It's a quite complicated observable. It was constructed in such a way to reduce the theoretical uncertainties, not that you can get an easy feeling on how this looks like experimentally.
Okay, thanks.
So, yeah, I mean, there's not an easy way how to depict this observable, unfortunately. Yes, I'm sorry. Okay, but now the good thing is, despite of all these discussions on about how clean P5 prime and all the rest is, there are two observables which are really very, very clean and where there's no question about the theoretical prediction. The first one here is RK, b2k mu over b2k-ee. And because both the muon and the electron can in principle be assumed to be completely massless compared to the b meson, the form factors here drop out to a very good approximation. In fact, this line here at 1, the thickness is already bigger than the standard model error. So there's really no question this is a clean observable within the standard model. And then what you find here is something like 20% deficit in muons compared to electrons. And now the really nice thing comes about P5 prime before. So if you assumed that P5 prime, the origin of it is new physics, and you assumed that it's only in muons and not in electrons, this is exactly what you would have predicted for RK. And even RK is not the only thing. We have in addition RK star, and again, you see a deficit here. So I would say in retrospect, since RK and RK star agree so nicely with P5 prime, I think there is no good reason to doubt the error estimate in P5 prime because of this internal consistency. And you can even see this internal consistency much better if you look here at this model independent fit. I just chose one example, C9 versus C10. So these are just these operators which are parameterizing the effective interactions between a BS current and a lepton current. And what you see here is you definitely need some new physics in C9. The physics in C10 is optional, but then if you count the sigmas, this is 1, 2, 3, 4, this is more than 5 sigmas away from the standard model. Now, you might ask the question, how is this possible? Because none of the anomalies I showed you so far deviate by more than 3 sigma from the standard model. How can you get to something like 5 sigma? And the answer is, it's like if you do several measurements of Higgs decays, for example. So you can combine the Higgs signal strengths for leptons with the Higgs signal strengths to BB bar and so on. And even so, none of the signal strengths themselves is at the 5 sigma level. If they all show excesses and you combine them, you arrive at a higher significance. And exactly the same happens here. So all these different observables I showed you are in principle measurements of the same small set of Wilson coefficients parameterizing these effective interactions. And then this is how you end up at 5 to 6 sigma discrepancy here. Okay, this was the first observable. Here I spent really a lot of time because I think it's the most interesting and the most compelling one. But it's not all we have. So we also have the B to C tau nu transitions. So this is tree level in the standard model, so it's a completely different animal. In fact, these are even the most probable B decays if you go to light leptons here. And they are even the decays from which you extract the CKM elements in case of light leptons. So for light leptons, it's safe to assume that you have no new physics. But for heavy leptons, there can be some new physics, apparently. Even though, as I said, this is not the place where you naturally expect it. But if you look at the measurements, then it looks quite compelling. So here is the measurement of RD star, B to D star tau nu over B to D L nu, where L is either muon or electron, and the same for a D instead of a D star. And now what you see here is this Bell measurements and also this LHCb measurements. the central values are somehow consistently above standard model prediction, which is in this case this black cross. So this time it's differently. The black cross is not the measurement, but the prediction. And the ellipse is not the prediction, but the measurement. So here you see the combination, and this lies something like 3 sigma above the standard model prediction. Since the tau, you cannot assume it to be completely massless. The dependence on the form factor doesn't drop out here exactly like for RK star, but you see you get a reasonable error. It's not too large. And as I said, you have this something like 3 sigma discrepancy, and what you need is something like a 10% constructive interference at the amplitude level in order to account for it.
May I ask a question there? So what are the prospects of Bell and improving on this measurement, and how fast that will happen then?
I don't know how fast. I mean, in principle, they should have already done it if you believe them what they said 5 years ago. But I mean, it's not a difficult measurement for them. So right. I think after 1 year of running, they should already have the accumulated luminosity to give a measurement at the same prediction as the old Bell and Babar measurements. And what I think is even more important is that they can measure B to tau nu very precisely, where we don't have these problems with these stars and with the form factors. So right. I think that after 2 years plus the time they need to do the analysis, who I really cannot tell you how fast it is. I mean, if you look at LHCb, it seems like you have to rescale everything you expect by a factor of 5. I hope this is not what will, I hope this is not what will happen with Bell, but if you just look at the data after 2 years, it should already be enough to see what is happening, what is going on here.
Okay, very good. Thank you.
One thing which you can do here already at LHCb is looking here at this arc-shaped psi, which attests again the same fundamental current. And the good news here is it goes in the right direction. So this arc-shaped psi is supporting the RD star measurements. And also here we are hoping for a R lambda B. But again, I really don't know how long it will take LHCb to release this R lambda B. I mean, everything takes apparently longer than expected. And I even have the hope, I hope I'm not upsetting any experimental audience, but I have the feeling they are happy about COVID because it gives them a good excuse why everything is taking so long. Okay, then the next anomaly is the anomalous magnetic moment of the muon. So this is a very long-standing anomaly. It goes back to 2006. The problem is we only have a single measurement from BNL. The theory prediction is challenging but sound. So just this year, they reached finally a theory consensus, which deviates 3.7 sigma from the experimental measurement. Now here, what you have to take into account is in the standard model, it's generated by these diagrams. And this discrepancy is of the same level as this electroweak loops in the standard model. So if you want to explain this discrepancy with new physics at the TeV scale, you already need a factor of something like 100 enhancement, because you need to compensate for the factor of mw squared over lambda squared. And so what you definitely need here is what is called chiral enhancement. Otherwise, with TeV scale new physics, you cannot explain the anomalous magnetic moment of the muon. And what you also have here is a small tension in the anomalous magnetic moment of the electron, which interestingly has opposite sign. So I mean, it's around 2.5 sigma, not that significant yet, but that it has opposite sign is quite interesting for model building. And I heard that they did the new measurement of alpha from cesium atoms, which is at the moment the best determination of it, and you could further improve. And with this now even better determination of alpha, you could get a better significance for the prediction of the anomalous magnetic moment of the electron, and then we should see what is happening. So they apparently already submitted it to Nature, but it will take something like we have to wait if it gets accepted to see what the number here is for the cesium measurement.
So
Okay.
no rumor, right?
No rumor about this, and definitely no rumor about the anomalous magnetic moment of muon measurement, because nothing is unblinded yet. So they hope to unblind in January, but even this doesn't seem certain to me anymore. And then after unblinding, they will at least take another 6 weeks to publish the results. So let's hope. At some point, I always think it must be released. So, but what I also want to tell you now, which is not that well known, is the Cabibbo angle anomaly. And the interesting thing is that also this Cabibbo angle anomaly can be interpreted as a sign of lepton flavor universality violation. So what you can do is you determine from super loud beta decay VUD, and if you assume CKM unitarity, then you can convert this into VUS, and you can compare it to VUS from kaon or tau decays. And then you see what is happening here. This is VUS from KL3 decays, VUS from tau decays, VUS from KL2 decays, and this is what you get from super loud beta decays taking different sets of radiative corrections. So again, these names are called after the collaboration which performed it, but what you see is that this is just above what you get from kaon and tau decays. Now you could interpret this as a violation of CKM unitarity, but you can also interpret it as a sign of lepton flavor universality violation, which I think is very interesting in the context of what you heard before. And the way this goes here is that here, for example, in K2 mu nu or pi to mu nu, you have only muons, while in beta decays, you of course have only electrons. So if you only modify the electron or the muon coupling, then you change these different determinations again, relative to each other. And with lepton flavor universality violation, you can explain this Cabibbo angle anomaly, which I think is really interesting. Okay.
Question on that slide? A quick question, if you can go back to the last slide. What does it mean to interpret it as a sign of CKM unitarity violation? Is that you need a fourth generation or something?
Yes, you need a fourth vector-like generation. Exactly. Because then you don't have the unitarity relation between US and VUD anymore. So this is broken by the fourth generation effect. And then you can also, because this here comes from VUD, and then it doesn't correspond directly anymore to VUS, and then you can also bring them into agreement.
Huh. Gotcha. Thank you.
Okay, you're welcome. Thanks for the question. Okay, and then this brings me to the summary for all of these hints for lepton flavor universality violation. So the general picture here is, for taus, you have large deviations at the absolute level, but the significance is not so high because data is not so great. For muons, you have new physics, medium-sized new physics, but very high significance because data is so great. And for electrons, we don't know yet. Maybe there is some new physics, maybe not. But what is definitely common about all this new physics is that it must interact really differently with electrons, muons, and tau leptons, and therefore break lepton flavor universality. Any questions so far? Now I have to look. Okay. So I have something like 15 minutes left, right?
Yep. We started a few minutes late if you want to, if you need some more.
No, it's fine. I think I don't need to go into too many details in what is following. So this was the real general part, which I think everyone can take home, so that these anomalies are very interesting and they all fall into the common pattern of lepton flavor universality violation. And now for the remaining 15 or 20 minutes, I will come to a little bit more specialized part where I want to tell you how one could explain these anomalies.
You know, larger than 5 sigma usually is associated with discovery.
I know.
Right? So how do we interpret this larger than 5 sigma? Why is the community not convinced of it? Or there are 5 sigmas or 5 sigmas?
I think the reason is mostly because we don't have experience with indirect discoveries of new physics. So the community is skeptical because we haven't seen a bump yet. So we haven't seen really completely ambiguous. Even so, from the statistical point of view, it should in principle be considered the same. But as I said, we don't have much experience with it. So people want to stay on the safe side and wait for confirmations from independent experiments.
I see. Very good. Okay. Thank you.
Okay. Is there a particular energy scale that these various hints are pointing to?
So the good thing is it cannot be very heavy. So it should definitely be something at the multi-TeV scale. So it depends on which anomalies you want to talk about. So I will come to this later. So B to C tau nu, this really requires new physics below the 10 TeV scale. Also the anomalous magnetic moment of the muon, because you need this chiral enhancement, and this chiral enhancement cannot be arbitrarily large, because it can maximally be V over, so the electroweak BeV over the muon mass. So it can be something like 1000, but it cannot be arbitrarily large. So if you take the square root of 1000 and multiply it by the BeV, you arrive something again like 10 TeV. But here, for example, it could be heavier. It could, it's also something like 10 TeV for RVOS. But for B to S mu mu, if you are really unlucky, you do this with a Leptoquark with large flavor violating coupling, it could even be 50 TeV. But I mean, it's not like with neutrino masses that you can postpone it to 10 to the 14 TeV. That's impossible. It must be at the multi-TeV scale. So it's a very good way, if you confirm these anomalies, to build a convincing case for future colliders.
Very cool. Thank you.
Thanks for the... Okay, so as I said, in the remaining 15 minutes or so, let me come to possible extensions of the standard model to account for these anomalies. So for RD star, it's difficult and easy at the same time. So it's tree-level within the standard model. This means you also need tree-level new physics to get this 10% effect. There's no way around. Now you need a charge current, so you are not left with many possibilities. It's just a charge 6, a W prime, or a Leptoquark. Now charged Higgses have scalar couplings, and the scalar couplings don't work because of Q-squared distributions or the b-sub-c lifetime, where they give an enhanced effect. The W prime, if it is right-handed, then you also have a right-handed neutrino here, then it doesn't interfere with the standard model, and then you need light masses and large couplings, you get problems with LHC searches. If it's a left-handed W prime, via SU2 invariance, it always comes together with a left-handed Z prime, and then it's ruled out by proton-proton going to Z prime, going to tau pairs. So this also doesn't work. So the only possibility you are left with is a Leptoquark here. Also,
okay, let me ask a question, because I remember a year ago or so, we work on this with Mariano Quiroz and Marcela on, and there was a model based on right-handed currents, W prime. But we discovered that if the width of the W prime is sufficiently large, the LHC constraints are highly relaxed.
Yes, they are there. But then is it really still perturbative?
Well, it's in the boundary, right, of what you could consider. Yeah.
Okay, then, maybe I should mention this once more, because I think I was referring to some article of Admir Crellio. I think he worked on this, and in this article they claimed that they can exclude the W prime, but
okay, that's fine. I will take a further look. I don't remember now the argument.
So in your article, what was the mass of the W prime and the coupling?
Yeah, the mass was in the few TeV region, so I remember 2 to 3 TeV, and the coupling was a standard Randall-Sundrum coupling that is enhanced. Yeah.
Okay, so something like 10. So it's definitely
because it was a model in warp extra dimensions, not 10, but of order, I don't remember, of order 3. So so a strong coupling. Yeah.
So, okay.
I have to remember, but I remember that when we look at the constant, my comment was that if the width is sufficiently large, these term constraints maybe not totally avoided, but are questionable. So then, anyway, so just a comment, but I agree with your general comment. But
no, thanks. You're right. I didn't know about your article. I should probably add a comment here that with a large width it might be possible. I didn't know about it. Sorry.
No. I'm not complaining at all. I just mentioning this as a comment on it. Okay, thank you.
In principle, it's a good idea. I mean, right-handed neutrino is quite natural, and in a RS model, you get your W prime with the right-handed neutrino together. So it doesn't seem to me like a very ad hoc explanation. So it might be easier to get what you told me than a Leptoquark. So it looks to me like an interesting possibility.
Well, take a look and then we can discuss. Okay.
Yeah. Okay, but I will focus here on Leptoquarks because the Leptoquarks also work nicely for B to S mu, but there are also composite explanations of B to S mu with Z primes. So I don't know, Carlos, if you looked at this in your model, can you also explain B to S mu?
Yeah, it happens because it's an SU2 cross SU2 model.
Yeah.
And then, you use the usual standard Z prime interactions so it works more or less. So it works miraculously for everything. But again, my problem with this model is that the couplings are large, and then you are uncomfortable while dealing with these large couplings in a total perturbative way, and then that's why I don't want to put too much emphasis on our work. But I think that, yeah, if you believe the perturbative calculation, you can explain everything. Yes.
Yeah, but I mean, that's a quite nice setup. I mean, it's probably more minimal than most of the models I have seen here.
Well, take a look and then I'm happy to receive your comments and criticism.
Okay, I will have a look, thanks.
Yeah.
Okay, then moving on to B to S mu. Here, the simplest possibility is definitely this Z prime. I mean, there are so many articles. I just mentioned the very first one, which can explain also RK. The problem about the Z prime is always you necessarily get an effect in BS mixing. There's no way around, because if you just double this vertex here on the left, on the right, you get BS mixing. You also have quite strong collider constraints because you can produce the Z prime in the S channel. And in fact, this already tells you that you cannot have minimal flavor violation. You need something where you suppress the couplings to the first two generations of quarks. Otherwise, you are dead from LHC searches. You can also do it with loop contributions, having new scalar fermions, 2 HDMs, R2 Leptoquarks, Z prime coupling to tops. I mean, since I also worked on this, I think I can fairly say that none of these loop solutions is really convincing to me. What works very nicely, maybe even too nice, are Leptoquarks, because you get the effect where you want to have it, but you don't get it anywhere else. So it's a little bit boring, because in this case, you don't predict other signals which you can test somewhere else. The Leptoquark could even be something like 50 TV, then you might not even see it at an FCC-hh. So explaining only BS mu with Leptoquark is a little bit boring, but you see, explaining BS mu in general is much more easy than B2C tau. Explaining a mu and AE, I mean, a mu is such a long story. I didn't dare to mention any references here on the MSSM. I think Carlos and Marcela wrote already alone probably more than 5 articles on this. So in order not to offend anyone, I just skip the references. So MSSM still works, but you have to assume some non-minimal SUSY breaking mechanism, because if you have a common scalar mass, then the solution is already excluded by squark searches. But if you split the lepton from the squark mass, you can do it in the MSSM. All this rest here, scalars, Z prime, new scalars and fermions, it works. It's not very convincing to me, but of course, it's possible. What I like here are Leptoquarks, because they naturally give you an M top over a mu enhanced effect. So 1,600, this is really large. So for Leptoquarks, that's quite nice. And in fact, this is what you can see here. So the Leptoquarks predict this small blue boomerang here, where you can explain the anomalous magnetic moment of the muon. And in principle, the only way to test it is set to mu mu at T-lab. Then it would be this very small circle here. And if this small circle would, for example, lie here, then it wouldn't overlap with the blue boomerang, and this would exclude a Leptoquark explanation. While if it overlaps, it would be compatible with a Leptoquark explanation, even though, of course, you cannot prove it. But you see here, this is for a 1 TV Leptoquark. You only need couplings of something like 0.1. So even for 10 TV Leptoquarks, you only need a coupling of 1. So that's quite nice. For our VUS, again, several.
Sorry, I don't mean to take out of the. But what is exactly?
I'm happy about any question, please.
No. But I want to understand well. What are the quantum numbers of this Leptoquark?
So this is the scalar Leptoquark singlet. This
S1
Leptoquark, but it works exactly the same way for the scalar Leptoquark doublet. But you can only have these two ones are the only representations which can give you a chirally enhanced and top enhanced effect.
Okay, very good. Thank you.
So this has the quantum numbers of a right-handed quark in the MSSM.
Right, that's why I was asking.
Yeah, but thanks for the reminder. I should put the S1, I forgot. Thanks. Yeah, concerning RVUS, so this discrepancy between VUS from beta decays using CKM unitarity and the direct measurements of VUS. Here, as I said, you can interpret it as modified W-quark couplings. But what works nicely is the modified W mu nu coupling. And here, the important thing is the W mu nu coupling, not the W e nu coupling. And the reason for this is that you get, if you have a W e nu coupling, you also, so in both cases, W mu nu and W e nu, you modify the determination of the Fermi constant from muon decays. And then you get a counter term which you have to insert in beta decays. And if you do it with a W e nu coupling, the effect in beta decays and in muon decay is the same. It cancels out. But if you have a W mu nu coupling, you only get the counter term effect in beta decays and the effect remains. So with a modified W mu nu, not W e nu coupling, you can explain the Cabibbo angle anomaly. And what works quite nicely are just modified neutrino couplings. So you modify W mu nu and set to muon neutrino, but not muon pairs. This is important because otherwise you have strong lap bounds. But if you assume this, so in the effective field theory for the experts, it would be C1 equals minus C3, then you can do a very nice fit here. So this is the modification of the electron coupling, muon coupling, tau coupling. And what you see here is that you can do more than 4 sigma better than without this modification. So that's also already a quite significant hint towards new physics, because you don't only explain this RVUS, this beta decays, you also improve at the same time the global electroweak fit, especially in the lepton asymmetry AL. And then if you add up all of this, you arrive at more than 4 sigma. So this I also like, and especially what I like here is if you look at the values, so these modifications here are at the per mil level. So you really don't need huge new physics to do this. So if you remember on B2S mu, you needed 10-20% compared to a stand-up model loop effect. In anomalous magnetic moment of the muon, you needed 100% compared to a stand-up model loop effect. And in B2C town, you needed 10% compared to a stand-up model tree-level effect. And all of this is not so easy to get, but these few per mil here, these are quite easy to get. Okay, then I have something like 5 minutes remaining. So in this 5 remaining minutes, let me quickly discuss simultaneous explanations with the Pati-Salam Leptoquark, which I really like. So the Pati-Salam Leptoquark is the Leptoquark you get within the Pati-Salam model. It's a vector Leptoquark SU2 singlet, and it has many very nice properties. So it couples left-handedly to b-sμ, so you get a nice fit to b-sμ data. It has a left-handed vector count in RD star. You predict RD over RD standard model equals RD star over RD star standard model. Again, a nice effect. Very importantly, it does not give an effect in B2S neutrino antineutrino, which normally...
Singlet, you mean SU2 singlet?
Sorry?
Singlet, you mean SU2 singlet?
Yes. So a singlet of SU2L.
So you have a left-handed effect because
you have two effects. So you can couple two doublets to this Leptoquark, so a lepton doublet and a quark doublet. Or you could also couple a quark singlet to a lepton singlet. Both possibilities work, but the right-handed count you simply don't need here.
What is the charge of this singlet?
The charge is just what you do is you couple a neutrino to an up quark, so it's plus 2/3, plus or minus 2/3.
Okay, very good.
Okay, so you don't get an effect in B2S nu just because of the charges. You don't get an effect in proton decay because it cannot couple two quarks. It can only couple quark to lepton, not quark to quark. So you're automatically free to proton decay for all orders in perturbation theory. It's in the nice Pati-Salam model, but now the problem comes, it's a massive vector boson, so not renormalizable without a Higgs mechanism. And in the standard Pati-Salam model, you are killed by orders of magnitude because of K to mu E. Because down is in the same multiplet as E, while straight is the same multiplet as mu, so you have to do quite some work on model building. But assume for the moment this can be done, and it can be done, then it's a nice explanation of RD star. So this is the coupling of third generation quark to third generation leptons, second generation quarks to third generation leptons, and you see here you can nicely explain B2C tau nu without violating B sub S to tau tau, LHC bounds, or loop effects in B2K star nu. It works. What it predicts you is an order of magnitude, several orders of magnitude enhancement in B2S tau tau processes. So this is still not excluded by LHCb, but it's within the range of LHCb or CMS Park B data. So you might find this soon. And what I really like, and this is the last point which I would like to finish, is that there's a correlation of this explanation here with B to SLL data. So via SU2 invariance, from the B tau C nu coupling, you get a B tau tau S coupling. This is exactly what gives you this huge effect in B2S tau tau processes. And then you can close this loop, attach an off-shell photon and a lepton pair. And then what you get is a lepton flavor universal effect in C9. And this effect goes in the right direction. So it helps you to explain P5 prime, B sub S to phi mu mu. It cannot explain RK star. But for this, you also have a tree-level effect at your disposal. And in fact, if you do this, you get the scenario which fits best to BSLL data at all. So you can even do 7 sigma better than the standard model. And what I would really like here, that neither the sign nor the size of the effect was predicted. But if you look here, the RD star together with this tree-level effect gives this preferred yellow region for B2SLL, which perfectly overlaps with RD star without violating other bounds. So this is really nice. This was just to tell you that you can do such a model building. I did it in the Pati-Salam Randall Central model. So Carlos, maybe we can even combine this with your model. And if you add both effects, maybe you are even safer from LHC searches. Because also our problem was also because of LHC searches, we couldn't get the full effect in RD star, only something like a 7% effect. So maybe if we combine our models, it would have a nice outcome. Finally, I wanted to say that you can explain this Cabibbo angle anomaly together with BSLL data with a vector triplet, so W prime together with Z prime. Again, one might get this in extra dimensions. I just had a sign problem so far, so it might not work, but maybe again, Carlos can help me with this. And this then brings me to the conclusion. So you see all these different anomalies, they point towards different extensions of the standard model, which could be correlated. So by confirming or disproving them, you bring us one step closer to discovering what physics beyond the standard model could exist. Thank you very much for the attention.
Thanks very much, Andreas. If everyone, if you'd like, you're welcome to clap. Thank you. That was fantastic. Do we want to? Are there any questions before we transition into just a longer discussion, more general discussion?
Yeah. Can you go back to the Cabibbo anomaly? That is a very interesting one, in my opinion. Yeah.
You mean the last slide on it or the second to last on it? This one?
The presentation of the Cabibbo anomaly. Yeah. Yeah, this one, that one. Yeah. So you mentioned that actually the red dots come from unitarity, right? From assuming unitarity.
Yes.
But okay. And then there is the points move further and further to the left. Then we have this measurement from tau decays that is very far away. So yeah. when you present a model, so this explains essentially these measurements and how far away. So how do you make all this compatible with a model? That is.
So I cannot. I mean, in the minimal model, I don't make all of it compatible. So right. What happens is this determination from beta decays. This has an enhanced sensitivity by VUD squared over VUS squared. So if you have this modified W coupling, what mostly happens is you move these two ones to the left.
I see.
These here remain, but of course the tension is east. If you would like to explain also this, you would need a right-handed W coupling as well.
I see. Very good.
So I get this 4 sigma from easing this tension here by 2 sigma plus a 2 sigma improvement on the electroweak fit. If, as I said, if you want to get more improvement, you need more free parameters like right-handed W coupling.
Very good. But at the end, you should get well, okay. So forget it. So then I was going to say that unitarity should work. No, then.
Yes, I mean it's only a apparent violation of CKM.
Only yeah, correct. So then.
So
but the average. No, the average value of VUS moves. Then when you do this, or
it moves only slightly. So you see here this. The average value of VUS within the standard model is this black band here.
Right.
And if you move, and then within the new fit, this moves something like by 1 sigma here. So it moves to something like 0.225.
But it's consistent with unitarity. That is.
I mean, I assume unitarity.
You assume unitarity. Okay.
Otherwise, I could not correlate it. So I assume no right-handed W coupling and no forced generation of quarks which violate this. Yes.
Absolutely. Okay. Very good. Thank you.
I have a sort of a general question. Do you think there's much with any of these anomalies or all of them? Is there much progress still to be made in theorists calculating the standard model expectations better? Or do you think at this point we're really waiting for more data?
So here for this beta decays, it's definitely limited by theory. So you see these radiative corrections here are the issue. And this issue should really finally be resolved. So for beta decays, it's a theory problem. I mean, I'm doing DSM physics. I'm unfortunately not in the situation that I can do this calculation. I was told it's not easy, but doable. I don't know, maybe among of you, there are some experts who could do this calculation. I don't know. But we are really hoping that they finally settle down their discrepancies here. So these groups, there have been long discussions in the past and they still cannot agree who is correct. This is why I showed both of them. For the B to SLL anomalies, it's not a problem of standard model calculations. You might do a bit for P5 prime and so on, but and of course with lattice you can improve on B sub S to phi mu, but RK star is really clean, there you don't have a problem. RD star I think is also not a theory problem. In the anomalous magnetic moment of the muon, the situation is a bit more mixed. They finally came up with the theory consensus, but after the theory consensus was reached, or even before the theory consensus was reached, there was this BMWC lattice calculation of the anomalous magnetic moment of the muon, which doesn't agree with this consensus, even though the people of the lattice collaboration are within the committee who did this prediction. So it's a delicate situation here in the anomalous magnetic moment of the muon. So the lattice calculation is in tension with E plus E minus data. I don't really know how to say it. So yeah, there probably one should do some progress, but let's just hope that the new value moves so far away that it doesn't really matter anymore. And yes, then there are B to D and B to U transitions. These are theoretically more challenging. So here you should again look at the theory side. And then, of course, it's a question also of model building, which is, of course, also partially my job. You see, no model came up which can really explain everything. But you see this Leptoquark composite stuff, this might go in the right direction.
Awesome. Thank you.
And you say something about, you were mentioning some UV completion with RS at the very end, and you went very fast, actually.
Yeah, I didn't want to bother you too much with details, so I'm grateful for the question. So what we did here is we just broke the Pati-Salam group, SU4 cross SU2 left cross SU2 right, down to the standard model group on an extra dimension, and on a compact extra dimension. And the nice thing is, what you get from this is you get excitations of all standard model particles. So you get vector-like quarks, vector-like leptons, Z prime, W prime, and you also get a vector Leptoquark. But the vector Leptoquark corresponds to the broken generator, so there is no light standard model scale Leptoquark. So this is quite nice. And what is also nice is that you have all the particles you need. You need these vector-like quarks and leptons to get Flavour non-universality, so they are automatically included. And you have the vector Leptoquark together with Z prime and W prime, which can explain the anomalies. As I said, the problem are LHC searches, mostly because of the KK gluon. This is why you can only get to 7% effect here. But we also have a right-handed W prime, like Carlos has in his model. And we also have a right-handed neutrino. So in combining this model with Carlos ones, I would hope that you can get a bigger effect.
Yeah, my model is with Marcela too. Then,
okay, I didn't know. As I said, I haven't seen the article, so Marcela.
No. I just because.
Yeah, but I mean, this might be promising. So we can only account for 7%. So if you can account for another 7%, it's perfect, because we have all, as I see it, we have all the particles you have as well, just in addition this vector Leptoquark.
Okay.